So I'm here basically, I just started recapping the basic continuous variable quantum computing concepts just to help me refresh my mind in terms of, to then approach in the next videos the actual yellow submarine project and then the research around it. And I just realized I was not recording, but now I'm recording. So basically, just went through the introduction and a bit of the Q mode. So yeah, Q modes, I remember, as a physical system, we can use a quantum harmonic oscillator as a model that allows us to investigate the state of a continuous variable quantum system and its associated Q modes. In general, for each state of the system, there is an associated Q mode. Therefore, we make no distinction between state and Q mode when there is no risk of confusion. Okay, it's a bit confusing because the state in discrete quantum, in discrete variable quantum computing, the state is the state of your whole system, and then the qubits are part of the state. They have multiple qubits that give you one state of the system, whereas here they seem to indicate that each Q mode is in a particular state in itself. Okay. When there's no risk of confusion, mathematically, if the system has a Hamiltonian edge, then it is described by the following. Okay, the sum of the different Hamiltonians. Okay, the Hamiltonian edge k denotes the Hamiltonian of the kth harmonic oscillator among n Q modes. So literally, it's the system has a Hamiltonian which is the sum of all the Hamiltonians of the Q modes it's made of. From elementary quantum mechanics, we know. Yeah, elementary quantum mechanics. The Hamiltonian of the quantum harmonic oscillator is given by assuming unit mass. In equation 2, where is equation 2 when you're starting with equation 4, my friend? Whatever. WK is probably equation 5. So this maybe is a typo. I don't know. I should be starting from 1 probably. This is equation 2. It's the frequency of the kth mode. The position xk and the momentum pk operators of the kth mode obey the commutation relationship. Blah. So you've got here different components, I see. Okay, so basically you're defining the Hamiltonian as a function of frequency, of position, and momentum of that thing, of that physical device, which is then a, what do they call it, quantum harmonic oscillator. Just let me quickly check. I'm not so sure. You won't see that because I can't switch tabs easily when I'm recording. But where's the quantum? What is a quantum harmonic oscillator? It's a quantum mechanical analog of a classical harmonic oscillator. Because an arbitrary potential can usually be approximated as a harmonic potential. It's a model. Okay, so it's a most important model system in quantum mechanics. It is one of the few quantum mechanical systems for which an exact analytical solution is known. So is it just a wave function? Is it that? Quantum mechanics. I'm looking at these, by the way. I'll just reload it here because it's just a model. It's just a way to model a wave function, or what is that? Gaussian states. Whatever, but it seems to be the case. Oh, and of course it goes back to the very beginning. I won't go to the appendix. Zoom in a little bit for you. So we introduced two new sets of operators defined in terms of xk and pk. Quadratures of a single Q mode k are defined as follows. Okay, so those are called quadratures. The position quadrature, the momentum quadrature, I assume. The Hamiltonian can be defined in terms of these quadratures. Okay. They're called quadratures because they are then here squared, or what? The quadrature operators obey the commutation relation. Since they are Hermitian, this is something I still have to dig into this. It's also appearing in the discrete version of quantum computing. They correspond to physical observables that can be measured. Okay, so basically you can measure position or momentum. Okay, but it makes it, I have to admit, it makes it much easier. I don't remember how did I react when I read all of that stuff, but I'll go back and watch the video. I think it had to be a lot of fun because now I'm a bit more familiar with the Hamiltonian concepts, with these whole things, and after having digested that and really having put the project aside for some weeks, now it feels a bit more comfortable to read that. So you've got position, momentum, this oscillator is the Q modes and the Hamiltonian and blah blah blah. Even if you don't really care about the actual formulas in here. The quadrature operators obey the commutation relation. Since they are, I mean, whatever that means, since they are Hermitian, they are from the physical observables. Vacuums. There exists a special state that corresponds to the lowest energy state of a quantum harmonic oscillator. This state is the vacuum state, also called the ground state, and I guess it's per each Q mode value. The state is important because coming from classical mechanics, we assume that a vacuum has no energy, but in quantum mechanics, the vacuum actually has energy, and we must take that into account in continuous computing, quantum computing. This is best demonstrated in the analysis of a beam splitter. If we send a photon in one port of the beam splitter, but not the other port, our analysis must treat the unused port as a vacuum, and if we require the use of the Hamiltonian of either port, the Hamiltonian of the unused port shall not be zero, but will be constrained by the Heisenberg uncertainty principle. Interesting. So vacuum, it doesn't mean no energy. Okay. Gaussian states and operators. A certain class of states, the so-called Gaussian states, are extremely important because they are easy to efficiently produce in the laboratory. This is important because while we know the Gaussian states are not enough for universal computation, we still want to investigate what can we accomplish with them alone that we cannot accomplish classically. In this section, we introduce and describe Gaussian states and Gaussian operators. Functions, okay. Gaussian functions. Found under the name of normal distributions in mathematics literature, Gaussian functions occur in striking regularity throughout science. We have already encountered phenomena whose state is described by a Gaussian function, the vacuum state. A multivariate Gaussian function has the following form, where x and b and where x equals this, b equals to that, and a is an n per x positive definite matrix. Okay, so no details. Wigner function in 1932 in a paper titled On the Quantum Correction of Thermodynamics Equilibrium, Wigner formulated a function which is quasi-probability distribution for multiple particles. For a single particle in the x basis, the Wigner function has the following form. We should not solve this function from the quantum state, but the reader is invited to understand what it means. The Wigner function is a quasi-probability distribution that describes the effects on quadratures. If the solution to the Wigner function for a particular quantum state in a given basis has the form of a Gaussian function, we say that such state is a Gaussian state. Okay. This function belongs to a wider class of functions called quasi-probability distributions. Okay, so that's just all, I think, all kind of I needed background for now. Gaussian states. Gaussian states occur in three main ways: as pure coherent, as pure squeezed, or as squeezed coherent states. I remember there's something like coherent states are states of minimum uncertainty equally dispersed among the quadratures. They are created by applying the displacement operator to a Q mode in the vacuum state. This means that the vacuum state is also a coherent state because it can be obtained by applying the displacement operator. So you apply displacement gate to a vacuum and then you get a coherent state. This means that you get minimum uncertainty in both position and momentum. Squeezed states refer to states where the quantum fluctuations in one quadrature are reduced at the expense of increasing uncertainty in the conjugate quadrature. Okay, so all this is saying is if we just assume we have it's two quadratures, position and momentum. So if you squeeze a state, it basically means you're increasing, you're reducing uncertainty in one of those quadratures, and one of those two, yeah, they're called quadratures, I guess, yeah, but increasing uncertainty in the other one. Squeeze coherent states refer to states they have displacement operator applied to the vacuum, followed by application of the Q. I guess they mean by the application of a squeeze gate. displacement operator applied to the vacuum, followed by the application of the Q mode. Okay. Gaussian operators. An operator is Gaussian if it transforms the Gaussian into a Gaussian state. Okay, makes sense. We mentioned two, displacement and squeezing. In the preceding section, now we'll elaborate on them and we introduce two more: the single mode rotation and the two mode beam splitter. Okay. Displacement. So the displacement operator increases the measured position by alpha real and the measured momentum by imaginary alpha, the imaginary part of alpha, for alpha being a complex number, sorry. Its action on the position quadrature is given by this, and the momentum quadrature is given by this. In the matrix form, taking this and replacing the identity matrix with 1, the displacement operator acts as follows. A real value vector of the measured position and momentum. Okay, so yeah, displacement. So it adds the real component of your complex number to the position and the imaginary and the complex component to the momentum. But I don't know how this is increasing the uncertainty in one place and decreasing it in the other. The squeezing operator, oh no, that was the squeezing operator, sorry. The displacement is actually minimizes that. Minimizes the uncertainty, okay. At least that's what I understood here. It's the coherence sequences between the applying the displacement operator. What was written? What was written? Or that was just a coherent definition of coherent state. No, that's a coherent state with minimal uncertainty. Equally dispersed among the quadratures. You can create it by applying displacement to a vacuum. Okay. Interesting. The squeezing operator. Squeezing operator with squeezing parameter R reduces the uncertainty in either position or momentum well below the standard quantum limit, while increasing the uncertainty in the conjugate variable. Its actions is given by these. Okay, these, and in the matrix form, the squeezing operator acts as follows: x prima p prima, and then yeah, real value vector, yeah. Okay, so it basically squeezes, reduces uncertainty in position or momentum and increases the uncertainty in the other. The rotation operator. The rotation operator rotates quadratures in phase space by a given angle specified from 0 to pi to 2 pi. Its action in the position quadrature is the following, and in the momentum quadrature is the following. Okay, they seem to be kind of like mirrored. Sinus and cosinus, and here's cosinus minus sinus. Okay. The beam splitter. The beam splitter operator is a two-mode operator that requires two Q modes to operate upon. It may be understood as a rotation between the two Q modes. Its actions on the position quadratures are as follows. So, and now I understand why they say the beam splitter is entangling them, because basically the effect on Q mode 1 is then actually depending on the position and the momentum of the Q mode 2, and vice versa. The position of interesting, of the position of the position of your Q mode 2 is now depending on the position and momentum of it's beautiful. Okay, that makes sense. Of the Q mode 1. So without really understanding those things in concrete, but you see that now they become dependent, so they become entangled. That's why then people say that with a beam splitter you entangle two Q modes in continuous variable quantum computing, which was a bit confusing by the time I think I was reading this. And a similar thing happens to the momentum quadratures. Okay, so I've got momentum, and then but then momentum is okay. Yeah. It's basically, isn't that, I think, isn't this thing here the same that the rotation? I see. Okay, so it's kind of a conditional rotation. It's funny because what you used to entangle in uh, in the discrete quantum computing, it's really also a controlled operation, right? So you're controlling an x rotation on a z value, not the other way. Wait a second. Yeah, and so here you're controlling basically. That's beautiful. It's a rotation. Ah, so that's like a okay. Look at this. Ah. So that's you're controlling a rotation on the position, phase rotation of the position as a function of that thing here, which is then interesting. There's a bit of an analogy in there. Okay. In matrix form, the beam splitter acts. I can't really explain it into a technical details really, but there's really an analogy there. That's interesting. That's interesting. So matrix form, got it in here. Non-Gaussian state operators. We'll not have much to say about non-Gaussian states for Manga, but mentioned two non-Gaussian operators and technical challenges around the implementation. Non-Gaussian states are simply where the Wiener function does not result in a Gaussian function. It can be created when non-Gaussian operators act upon Gaussian states. Non-Gaussian operators, they do not return a Gaussian state when given to a Gaussian state. The Kerr operator and the qubit phase operator. Okay, interesting. And I think we're almost done with the measurements then. Non-Gaussian operators are ones that do not return a Gaussian state when given to... The cubic phase operator, V whatever, can be understood as the result of the following process. Prepare two Q-modes in the vacuum state. Apply a two-mode squeeze operator on both Q-modes. Is it a two-mode squeeze operator? Something like it? No, it's not a beam splitter. Something. Okay, on both Q-modes. Then apply a large momentum displacement on the first Q-mode. Lastly, perform a photon counting measurement on the first Q-mode. This results in the second Q-mode behaving as if the cubic phase operator was applied to it, and its state may be called the cubic phase state, which is a non-Gaussian state. The action on the position quadrature is given by action on the momentum quadrature is given by. So it just affects the momentum. That's basically what this is saying, because this is. Is it? It seems like so. You apply a two Q-mode squeeze operator on both Q-modes. Then apply a large momentum displacement on the first Q-mode. Lastly, perform a photon counting measurement on the first Q-mode. Counting. So you're counting. If you're counting, natural number n. Photon counting a single Q-mode, preserves the Gaussian character. Okay. The Kerr operator be defined in terms of quadratures. N is called so nk. Kerr operator. What the hell is this? This definition is not even useful. In terms of quadratures, n is called the number. N is called the number operator. We then proceed to define the Kerr operator with reference to the number operator with parameter k. Do whatever that means. I gotta do a bit of a more dig into this, I guess. But I can do this as I work through the actual architecture and the actual code and how is this. But that basically gives me, I think, a rough idea. And then measurements. So there's just a bunch of weird operators in here. And the measurements. So you can do different measurements. Photon counting. So you count, I guess, the amount of photons, and then you get like a real, and that's real. Homodyne detection. Photons are captured by a photodetector, which converts photons into electrons. it turns into electric current. This electric current is generally proportional to the number of photons. We wish to detect the quadrature of the Q mode under consideration. To accomplish this, the Q mode is combined with the 50-50 beam splitter. Then the two output Q modes of the beam splitter are the ones that are converted to the photocurrents, and their difference is measured. The quadrature of choice is measured by introducing a phase in the beam splitter, which is varied to select the quadrature. Harmonic detection is a projective Gaussian measurement that projects Gaussian states into Gaussian states. So is this saying that this is something you can use then to measure either the position or a harmonic detection allows you to then measure what's the position or what's the momentum? I think so. We wish to detect the quadrature of the Q mode under consideration. I don't care right now how it is implemented, but and then okay, heterodyne detection. Heterodyne detection is a measurement of both the X and P quadrature simultaneously. This results in uncertainty in the measurement of quadratures, as with homodynamic projects Gaussian states. Okay, that's it. We made it in under 30 minutes. It's cool. Yeah, I didn't have much time, but it was more of a recap. I really kind of went a bit deeper into this, and I think I even checked sort of the Xanadu documentation and stuff. But basically, in the next videos, I'm really going to go through the actual architecture of the QAOA example they're building, because it's referenced in other papers, and then I'll probably dig deeper as needed. But I think I mostly remember. So you've got momentum, you've got position. Those two things are real numbers at the end of the day. And then you've got different ways to measure. You can measure photon counting. I'm not sure what is this useful for. And then you can either choose to measure position or momentum, and you can choose, or both at the same time. But this creates some kind of uncertainty. I don't know what it really means in here. Maybe as that you don't get exact measurements. Maybe you just get a probability distribution or something like that. I don't know. This is something to dig into as well. But cool. So that's basically, there's a lot of an analogy to the quantum, to the discrete quantum computing. It's just that you're using, it's really coupled to a specific implementation, because that's literally, we're talking about photons, right? So you've got momentum and position and these quadratures and then these different gates and whatnot, and then. But it was nice to see how the beam splitter creates entanglement, because it basically rotates a Q mode as a function of something else from the other Q mode, so to say. So then the one value depends on the other one as well. So this is how you're kind of entangling it. That's the equivalent of applying a Hadamard gate, right? And then that Hadamard gate is sort of a rotation, but then that Hadamard gate that's rotating, you basically, after that, you apply a control knot on another qubit, and then the value of one becomes dependent on the value of the other. So pretty cool. At an intuitive level, I think it's good. It's a good summary. Let's see now how much farther we have to dig down. But I think the next video I'll really go back to. So remember, there are two different papers that were referenced in here. One was a paper to encode the actual graph, and another paper that was actually based on a neural network design for continuous variable quantum computing. And I'm basically I'm gonna dig into the second one first. But I remember that I started with the other one and I didn't finish it, so I'm gonna try to start with the other one, see what happens. Cool. It's nice. Perfect.